Hi everyone, this is Renaud from Sevensense, which is a startup based in Zurich that builds the eyes and brains of autonomous robots. Today I'll present two building blocks of such robots, which are place recognition and collaborative mapping. I'll first show what we worked on at the Autonomous Systems Lab from ETH, and then how the Sevensense team built up on this more recently. Collaborative mapping, or large-scale multi-robot SLAM, is one important task for robotics. We have applications such as search and rescue, logistics, and also autonomous driving. Here you see two nifty robots, which we used in the Trader project, where the goal was to explore and map this decommissioned power plant. In such search and rescue scenarios, we want to map in 3D, as we're often dealing with uneven terrain. That's why we equipped the nifty robots with spinning 2D lidars, and we're also seeking a real-time solution as we want the whole system to run on these embedded platforms. This brings us to the goal of this work, which was to develop a real-time multi-robot SLAM system for robots equipped with 3D lidars. There are multiple challenges to large-scale multi-robot SLAM, and here we decided to tackle these three ones. First, we want to build a unified map, and for this we need to be able to recognize places. As usually we don't have prior information regarding the relative transformation in between the robots, we're looking for a global localization solution. Then, if you ever worked with 3D point clouds before, you probably know that building a single robot SLAM solution is already hard enough. So to scale this to multiple robots, we're looking for efficient algorithms. Finally, such multi-robot systems generate lots of data, and on top of this, we're operating in scenarios with limited bandwidth channel. So thus we're looking for a compact representation that can easily be stored and transmitted between the robots. When we started this project, we looked at the state of the art and we could identify two main families of techniques. First, we have the local approaches, where we usually take a full dense 3D point cloud. We then extract 3D key points, describe these key points, retrieve these key points in the database. And finally, there is a geometric consistency step, which outputs the localization. Then we have the global approaches, which is similar to image retrieval. So for the full point cloud, we extract one descriptor, which can then be used to retrieve the place directly in the database. And to output the localization, we usually have a geometric consistency test or a registration of 2 point clouds. Looking at the literature, we saw that both families have different drawbacks. So the global approaches are better in terms of local changes, but are less reliant to changes in viewpoints. On the local approaches side, we do better against these viewpoint changes, but they can also have a much higher computational costs. Obviously, it would be nice to combine the advantages of the two families, and then we started to ask ourselves if there could be a method that lies in between. So together with Daniel Dugas and our colleagues from the Autonomous Systems Lab, we developed the SegMatch approach. The idea here is to perform global localization based on 3D segment extraction and matching. This picture on the right shows segments extracted from the Kitty odometry dataset, each with a unique color. So why would we use segments? Well, first of all, we believe that they can offer a good compromise between local and global descriptors. Using segments, we do not rely on semantics, which mean on the presence of known objects in the scene. We also do not rely on a perfect segmentation, so even if two objects are segmented together, our algorithm can still work. And finally, as we will see later, the segment-based approach allows us to create a compact and descriptive map representation. Here's an overview of the approach. As an input, we assume a dense 3D point cloud, which can, for example, be generated by integrating single LiDAR scans. We first perform segmentation, and in this work, we considered two approaches based on region growing. Then each of these segments is described, in this case using a handcrafted descriptor. These descriptors are then retrieved in a database using k-nearest neighbors, followed by pruning. And finally, we have a Renzac-based geometric verification step, which then outputs the localization transformations. Here is one example of a correct loop closure in the Kitty dataset. In blue, we see the trajectory of the robot traveling from left to right. And on the top, we see a point cloud in color where all the segments extracted in the local map or the vicinity of the robot are depicted. In white, we show the target map against which localization is performed. The green lines indicate segment matches which led to a successful localization. You can see that we use different types of segments to localize, for example, parts of buildings, cars, and vegetation. So now we'll show a first demonstration of the SegMatch approach. In this case, we're doing global localization against a target map built from the Kitty dataset. So the target map is in white, the source map is in color above. And once again, we'll show with these green correspondences when there's a valid localization happening. We see that the localization system is running quite successfully. In the original SegMatch paper, we managed to have the system running at roughly 1 Hz. And now you see that it's running quite a bit faster, so I'll give you some more details about this later on. Once again, we're using different types of segments to localize, so vehicles, parts of buildings, and also vegetation. We use the same Kitty dataset to do a dead reckoning distance evaluation. And here we see in X the travel distance, and Y the probability of not being localized in the target map. And here the lower the better. So we see that all the different configurations of the SegMatch approach outperformed our key point baseline. With this, we proposed one solution to global localization that could operate at 1 Hz. And this brings us to our next work, where together with Mattia Golub and Hannes Sommer, we've presented an incremental localization technique which allows us to achieve better efficiency. I will only present the first part of this solution, which is an incremental region growing segmentation algorithm. So here you see a top-down view of a robot mapping its environment. So this is a small 2D toy example. In black, we show the voxels that are currently occupied in the voxel grid, and the circle represents the area that is considered for extracting the features for localization. So this is our local map. So first, we extract segments, and the descriptors are already included in the target map. This would then allow for other robots to localize themselves, again this one. Then the robot moves forward and makes some new measurements. We have now implemented a dynamic voxel grid, which tells us which voxels become occupied when new scans arrive. Our idea was to use this information when performing region growing by growing only starting from the newly occupied voxels. In some instances, we would discover a new segment. We might also grow from a newly occupied voxel to an already identified segment. And finally, these new voxels might also allow us to merge two segments together. So here is an example of two segment tracks which we identified with this algorithm, which we will then use later on. At the moment of writing the second paper, our best implementation of SegMatch was already running at 2 Hz. And with our contributions to the incremental algorithm, we could operate in real time with data generated by a Velodyne sensor. So now that we have an efficient global localization solution, we started the work of putting this together in a full multi-robot SLAM system. So this is work I did together with Abel Gavel from the Autonomous Systems Lab. And we opted for a centralized solution. So basically each robot would be responsible of pre-processing the raw data. And then the master computer has the task to co-register all the trajectories together and then also do the batch optimization. Looking at some details, we see that each robot is fusing IMU and odometry data together with running ICP on the point clouds. So this enables us to estimate the motion of the robot, as well as for creating a dense point cloud from which we then extract the segments and we do the segment description. So here we see that this is the only data that needs to be transmitted over the Wi-Fi, so the odometry factors, and also the descriptors and the centroids. And then the master computer receives all of this data, performs the segment matching and global localization, as well as the maintenance of the segment database that is needed for this. And the master computer also does the multi-trajectory estimation. So here we're using ISAM2 as a backend. We tested the system in a multi-robot search and rescue setup. So we took data collected at the Gustav Kneppe power plant in Dortmund, and we basically had 3 real firemen teleoperating 3 robots for the task of exploring this decommissioned building. This is how this experiment looks like. So we have the top-down view at the bottom right. And here we see in green, red, and yellow, the 3 trajectories of the robots being estimated in real time. And in white, we have the unified target map that is also built in real time. So we see that when we do associations between the different local maps, we're able to co-register the different trajectories. So this building was roughly 100 meters by 20 meters wide. And it also had 2 floors. So we see the robot with the red trajectory is currently starting to explore the second level. To the best of our knowledge, this was the first work to present a real-time multi-robot SLAM solution for a robot equipped with 3D Lidars. And we successfully managed to create this unified map representation. However, there's a little trick. So basically, if we want to be able to display this to the end users in the base station, we would need to transmit all of the point clouds. And from our experience in the Trader project in such search and rescue solution, it's not always possible to have a good connection that would permit this transmission. With this, we close the loop and complete our first iteration of our multi-robot SLAM system. To tackle the compact representation part, I worked together with Andrei Kramariuk, and we developed a data-driven approach to generate more powerful descriptors. The usual state-of-the-art way at that stage was to use this descriptor for the only task of localization. Here, we propose to use the same descriptor also to generate a 3D reconstruction of the environment. For this, we use an autoencoder-like structure, and this allows us to provide visual feedback to remote end users. On top of this, we can also do semantics extraction, and all of these features we get at the same price, which is a single pass of the descriptor network. Taking a closer look at our descriptor, we have 3 convolutional layers and 2 fully connected ones. We have a descriptor of size 64, and we have designed a combined loss function that allows us to address the 2 different objectives. On one hand, for better localization performance, we train the descriptor for a classification task, and each class contains different observations of matching segments. As you see here, we got this training data from our incremental segmentation algorithm. Then for reconstruction, we appended a decoder network, and here we use the binary cross-entropy loss function. Note that we have this autoencoder-like structure, which allows us to have these compact descriptors that can easily be transmitted. And then any agent in the network is able to take this descriptor, do a forward pass of the decoder in order to generate 3D reconstructions. And finally, we can get semantics by appending a very simple fully connected network. And in this case, we worked with 3 classes, which are buildings, cars, and others. Once again, we took the Kitty dataset to evaluate our system. So we took drive 00, cut it in 5 pieces, and played all the data back simultaneously on a single computer, which is then responsible for building the map. Here we see the different local maps that are being processed and then compressed to this handful of descriptor and segment centroids. And afterwards, we can then reuse these same descriptors used for localization to reconstruct the environment and also to extract semantic information. So here we show in blue the buildings, in red the cars, and in green all the rest. Once again, we're using K and N to retrieve the descriptors, and we have this geometric consistency test to output the localizations. Now we took advantage of the semantic information by basically doing the global localization by not using the segments which were vehicles, as these could be moving. So we are able to localize at 10 Hz with 5 different Velodyne sensors. And we only need 60 kilobytes per second to transmit the descriptors to the database, which is an effective compression of 44 times as compared to transmitting the full point clouds. Here are 2 other experiments where we achieved real-time performances using the same network that was trained on totally different data. The 2 reconstructions that you see here could be generated by decoding the same descriptors that were used for localization. Now we have a few examples of reconstructions which can be achieved with the SegMap descriptor. We have the 3 semantic classes which we mentioned before, so vehicles, buildings, and others. Next, we evaluated the descriptor retrieval performance using the Kitty dataset. This is the ROC curve with false positive and true positive rates on the X and Y axis respectively. We saw that we improved the area under the ROC curve by 28% over the baseline solutions. We also wondered how does the retrieval compares during the incremental segmentation process. So here on the X-axis we have the segment completeness. So at the left is when we collect a very first sample about a segment, and on the right is when the segment is dense and complete. On the y-axis, we have the number of neighbors that need to be retrieved before finding the correct segment in the target map. Also note the log scale, and in this case, the lower the better. We see that the eigendescriptors are not that well suited for this task, as often we need to retrieve roughly 100 neighbors before finding the correct match. Looking at the performance of an autoencoder, which is only trained for reconstruction, we see that it performs well, but only at later growing stages, so when the segment is complete. With our SegMap descriptor, we achieve a clear improvement in terms of retrieval for the complete growing process. This also leads to simpler geometric verification and better localization performances. So with this work, we have proposed a solution to leverage the compact capabilities of our segment-based descriptors, which also completes our full multi-robot SLAM system. Everything which I've presented so far is available open source, and we also received positive feedback from the community. For example, these 2 load closure examples, which were shared from users on GitHub. So all of this seems to work nicely, and of course we wanted to do even better. So this is the challenge we gave Sebastian Ratz when he joined Sevensense, and let me tell you, he really nailed it. All the techniques that I presented so far, as well as the state-of-the-art at that stage, relied on 3D dense point cloud. These are usually generated by integrating single LiDAR scans using a state estimate. Of course, then you would also integrate the errors when you accumulate the noisy poses. To address this, Sebastian proposed to drop the expensive integration step and then directly to use the single scans, such as the one on the right, which is a scan of a Velodyne VLP16 sensor. So this is where OneShot came from, so basically global localization using a single laser scan. There's a few advantages of this approach. So of course, first of all, we don't need to move to localize, so this makes the localization process safer and also reduces dramatically the dead reckoning distances. The solution we propose is lightweight and simple, so we don't have to mechanically actuate any sensor. This is an overview of the one-shot approach. So as I said, as an input, we have a sparse 3D point cloud. For the segmentation part, we used an algorithm presented by Bogoslavsky and Stachnis, which is based on the discontinuity of depth, which we perform directly on the range image to keep it efficient. On the description part, we use a CNN, which we adapted from the one of SegMap. And for the training, we have in this case considered a triplet loss and negative mining. Back to our dead reconning evaluation on the KT dataset. So again, we have in X the travel distance and in Y the probability of being unlocalized. Again, the lower the better. In blue here, we have our baseline SegMap, which uses 16 channels of the Velodyne. In orange, we are using 64 channels. We have a faster integration of the dense point cloud, which here results in better, but still not perfect solution. In red, we have SegMap again, and in this case, we assume that an integrated point cloud is always available. And here we would depend on the movement of the robot, and it's not exactly the kidnap robot problem that we are solving with one shot. And finally, we see in green that one shot performs very nicely. So in this experiment, we had 98% of the scans that can localize immediately without movement of the vehicle. On top of this, we proposed a strategy to increase the performance of the descriptor, this time using vision. So here we leverage both structure and appearance. So using a Lidar and a camera, we project the point cloud on the corresponding image. And then both the image and the point clouds are passed to a new neural network for extracting the descriptor. And here is this neural network. So we have the two branches computing intermediate descriptors. On the left, we have the geometric part, which is similar to the SegMap one. And on the right, we have the vision part, which uses NetVLAD, which is a popular network for image retrieval. And finally, we have a set of dense layers, which output our multimodal one-shot descriptor. So we have already used the one-shot approach in quite a few different applications. What you see here is data collected using an outdoor delivery robot, where one-shot successfully managed to localize 92% of the query scans. We also tested on the NC-LT dataset, which is a large-scale, long-term dataset with a lot of structural and appearance changes. Finally, we tested on yet another challenging dataset, this time which was collected using a handheld LiDAR stick in underground tunnels. And here we see that we also successfully managed to close a loop at this intersection of two tunnels. To conclude, we have presented a new approach to the place recognition problem, which is based on the extraction and description of segments. After this, we improved the efficiency of this first method, which allowed us to process in real time the data from 5 Velodyne sensors. We brought all of this together in a multi-robot SLAM system, which we also made open source. We also proposed a novel data-driven descriptor, which allows us to do more than just global localization. So basically, for the same price, we also get the 3D reconstruction and also semantics. And finally, we introduce OneShot, which is a global localization pipeline, which uses only a single LiDAR scan to operate. As you know, there are many other building blocks that are needed to deploy robots in the real world, and these are only a few that we are working on at Sevensense Robotics. For example, we have visual localization, dynamic detection, and planning and controls. I think that such innovations are the key to bring robotics in our daily life, and we're really convinced that this can have a huge positive impact on our society. Obviously, such a bold mission is only possible with a great team, and we're really privileged to be working on this together with amazing people at Sevensense Robotics. So I would like to give a big hands up to everyone at Sevensense and also to our colleagues from ETH Zurich for making this possible. I hope you found it interesting, and I'd be happy to hear from you again. So don't hesitate to drop me an email if you have any questions, or even better, if you want to join the team. Thanks a lot and enjoy the conference.